but in real life with the real data it's gonna be big. And for this second one, we are finding facilities with the highest ICU beds. In COVID, this was a big issue to get the beds and stuff like that. So we are also mentioned this in our query. This is the query we have written for it to find the highest number of ICU type of beds. So and this is the output we got of from our sample data.
Is your data, I know it's made up data, but is it like everywhere in the world, or is it focused anywhere?
It's many diseases, many places.
Okay.
So this is our third query, which healthcare providers are handling the most critical cases and which facility do they belong. As of this can be helpful for insurance or for the people who are getting insurance, no? So we have included this too. So that's the query. You can go through it, and this is the output that you are getting. So as once again I am saying that the data is sample, so it's getting least amount of outputs. So when we put in something good, we can get something good. So from now here on, Astik will continue. Hope you are enjoying the presentation.
Hello everyone. So after creating this database and loading some data in it and running some queries, as you all saw, then we went to the next step, that was creating the dimensional model or dimensional concept. So basically this in this we have around 6 dimensions and we have kept 3 to 4 fact tables, and overall it is following star schema. So let's go through it. So the first step was to know what the grain of this particular problem is. So we went and we just did our research and we found that for any disease tracking system or patient tracking system, the lowest of the lowest grain can be the patient itself. That who is the patient, what is the record, and all those things. So we created the patient, test, and date level to the final level of as the finest level of the granularity in any healthcare data system. So why are we using this particular grain? So we are using this to, as there will be detailed patient tracking and disease progression monitoring for any outbreaks or that can happen in the future, or to keep a track of the diseases.
Are you saying that disease progression monitoring is a different grain or the same grain? Or another case for the same grain?
Yes, another case for the same grain.
Okay.
Yeah. So these also can be done using the grains and this.
Mm-hmm.
Yeah. So we start with the dimension models. So this is our first dimension model, that is date dimension. So it stores all possible date for analysis, enables time-based analysis by year, quarter, month, week, helps track season patterns and disease outbreaks, allow weekend versus weekday comparison for hospital activity. So the second dimension is the patient dimension itself. So this stores patient demographics and classification with the address and all those things, and track changes in patient risk categories over time, what kind of diseases the patient have, and what all are the symptoms and what is the history of the patient. Enables analysis by age groups and risk factors, helps identify vulnerable population, includes slowly changing dimension type 2 to track history of the patients.
So this one's type 2, date's not. Right, date's not type 2. The date dimension is not type 2. Probably doesn't need to be, right? You don't have start date of the dates and date of the dates. Like if the patient makes sense, they could change their name and stuff like that over time.
So the next dimension is the disease dimension. So this particular contains disease and variant information of the diseases. This track changes in disease classification, enables analysis by disease type and communicability, monitor variant evolution and severity, includes historical changes of diseases, definitions and names.
So this is type 2 also.
This is also type 2. So a particular disease can be called something else 15-20 years before, and it can name change today. So the next dimension is the location dimension. In this, it stores all the geographical hierarchy, country, state, city, includes population and density metrics, enables geographic analysis of disease spread, helps identify high-risk areas and regions, and track changes in regional demographics. So that just comes under the population and all those things. So the next is the DIM provider. So provider is basically a healthcare provider. It can be an insurance company, the doctor you are going to. So this stores healthcare provider information, tracks provider specialties and experience, enables analysis of provider performance, monitors provider availability and workload, and maintains historical providing assignments. The next is the facility. So that is basically hospital and all. So this contains healthcare facility information, tracks facility capabilities and capacity, enables resource allocation analysis, monitors emergency responsible capabilities, and track changes in facility status. So all these the dimension table, all includes natural keys, IDs from source, and the surrogate keys. We have implemented it, and business attribute for analysis, historical tracking capabilities, current status indicators, relevant metrics for analysis. So we'll go on with the fact tables that we created. So that's the first fact table that we created, that is cases, fact cases tables. So basically it records individual patient disease cases, and the measures it has is severity of cases, length of stays in facility, treatment outcomes, treatment cost. And the business use for this particular fact table is to track treatment effectiveness, monitor healthcare cost, analyze patient's outcome, measure facility performance.
It's just like, is a case at a patient level?
Yeah.
Like it's a case for every patient?
Every patient.
This is the lowest level?
For just like we said in the grade, patient, test, and date. So what all the tests he had, and all those for the history of the patient. Fact cases. So sorry. So cases is the disease. The test fact table, it contains all the tests that have been done.
But per patient?
Per patient.
So in other words, if I have a cold, I'd have a record for that. If you're doing 5 tests for my cold, this would have 5 rows, where the other one has 1 row?
Yeah, I think so. Yeah.
Yes?
No, this will have, I think, sub-rows.
Sub-rows. In this, the
Yeah.
test one will contain all the tests of
Yeah.
the patient.
Right,
Each
so if I
case.
have a
If you
disease,
have it, yeah.
I'll be 1 row
You have
in the cases.
You could
Yeah.
do a test and not have a disease.
You could have a case and not have a disease, you could probably also have a disease and not have a test.
Test, yeah.
But usually, you would have more tests than diseases.
Yeah.
Yeah,
than
obviously,
cases.
that's all.
Yeah. So basically, this table it track all diseases testing activities, and it contains measures like test results, test types, testing costs, and the business use for this is to monitor testing patterns, track positivity rate, analyze testing cost, and measure testing efficiency among the providers. So the next is fact outbreak table. So this particular table, it helps monitor disease outbreak events, and the measure it have is total cases in outbreaks, mortality rates per disease, and economic impact and duration of the disease, or you could say the outbreak that have been in the history. And the business use is to track outbreak patterns for predictive analysis. We can use this assessment economic impact, monitor containment effectiveness, predict future outbreaks.
So would this, again, would this be, so for example, COVID,
Yeah.
that's an outbreak, right? So, or if I come in because I hurt my foot, and Ben comes in because he has a headache, that's not an outbreak, we wouldn't be
Yeah,
able to
that's
do it.
that's why we're tracking the total number of cases.
Right.
So that we have
So-
past
so
this
for-
number.
So in other words, what's the grain, is it also at the patient level, or is it the count of patients?
Count
For-
of patients.
So this is
Per
much higher,
region, yeah.
this is a much higher grade.
Yeah, per
That-
region.
That when it will be outbreak, we have a
So
higher rate.
basically-
So
yeah.
it would be like the outbreak,
Yeah,
Yeah.
and maybe that's it.
yeah.
On a big level, on a big scale of
Yeah, it's a
patient.
hi- it's
Region
a-
level, you could say.
Or, okay, like
Yeah.
outbreak in a continent. or
In a continent,
region.
in a state, or in a country.
Okay.
to analyze the trends of the diseases, what all the diseases are there in the country, and what are the most cases, these are things. So the next fact table is fact inventory table. So basically this table, it helps to track medical resource inventory for each and every healthcare provider. So this contains the measures resource quantities, resource value, day of supply, and resource types. And the business use for this particular fact table is to monitor resource utilization, track supply levels, optimize resource distribution, and to prevent stockouts.
This is not at a patient level, right?
Yeah, this is just to monitor the
It's
stock.
not at a patient level.
Yeah.
Some other fact tables.
No. So by implementing all these things, these are the key analysis capabilities we can do, or the person, our stakeholder can perform. It can perform the cost analysis using this warehouse. She can use it for resource utilization, disease spread, to check disease spread patterns, healthcare outcomes, facility performance, and provider effectiveness. So these are the six that we shortlisted, but there are vast many more than these. So after this, Emmanuel will continue. What is it? Okay, I'll continue. So sorry for that. I'll continue the next 3 slides. So basically, this slide it is showing the comparison between NoSQL and relational databases. So basically, as of now, our model, it is running on relational database, that is PostgreSQL, and the schema that you showed you earlier, ER diagram, represents a relational database model with clear defined tables, primary keys, foreign keys, and relationship. Each table corresponds to a specific entity in the domain, example, patient, disease, region, healthcare facility, and contains attributes relevant to that entity. So the key characteristics of relational databases is normalization, relationships, indexes, and joins. So if we chose to do this particular project on a NoSQL database, then we did our research and we came up with these particular key characteristics and a bit of couple of lines that shows that it says in a NoSQL database, that can be MongoDB and any other. So this schema would be more flexible and could be structured using documents or collections. The data model would likely use a denormalized approach to improve performance for certain queries and avoid joins. So the key characteristics of the particular NoSQL databases are collection and documents, schema flexibility, denormalization, and scalability of the project. So that's we did basis to our knowledge on the NoSQL. And these are the some tabulated, same thing in a tabulated manner that just shows the feature and the differences between relational and non-SQL databases. So you can have a look at it. It contains structure, feature, the normalization, joins, query language, scalability, flexibility, and performance, and use cases among relational and non-relational databases. So yeah, now Echo will continue. Thank you.
So hi, how's everyone doing?
Good.
I know it's a lot, but you're doing great. Anyway, so we thought about how to take this to an AWS structure, if you could. Azure, AWS, Google Cloud, it's all the same things, they just call the things differently. Someone wants to summarize cloud computing. At the end of the day, it's just someone else's laptop. So that's how you should think about cloud computing. You're using someone else's hard disk, someone else's space, someone else's, in this case, AWS's. So this is how we would kind of try to implement our system if we were to put it in the cloud. This you would have, of course, multiple. This is one short of a VPC, but you can have very many VPCs, virtual private. Of course, you'd have public subnets. We're going to go through all these in more detail, but this is an overview of. Okay, so the core infrastructure, you'd have, of course, multiple AZ deployment. This is multiple availability zones. So AWS, I don't know if most of you might be familiar. It's always best to have your thing in multiple availability zones. They have so many. Of course, with the public and private subnet, because you need to kind of store your data. Then you have an application load balancer. This is basically it's Christmas season, so all of you are going to go and start shopping Christmas hats. So the guy who sells Christmas hats, his traffic is higher now than it will be in March. So this is basically supposed to like kind of balance that load. If we get a lot of traffic, it knows what to do, distribute all this traffic. We have clusters for containerization, that's on the top layer. Lambda functions to just bridge everything together. Now on the data processing layer, we'll store all this in S3 because if it's a lot of data, S3 is always your go-to. Glue to kind of like extract and do some ETL processes like we did in the NoSQL. EMR kind of works between Glue and Aura, but at the end of the day, it ends up in an Aura database, which when we did our research, turns out is the fastest kind of DB that AWS has. And then, of course, we need this thing to be fast. This is storage kind of thing. Think of the batch layer as storage where this all going. So speed layer, you're looking at how fast is this structure. Kinesis data streams, this is the fastest they have to basically get the data from the database, have a Lambda function in between there to kind of work on it. You can add a DynamoDB layer on top because it's also really fast for tables and all these things. That's now your speed layer to make sure your system is fast and you can access it faster and all this. Then the serving layer, this is how you get this to the people. This for relation and this for non-relation in case you want. And of course you need Elasticache for performance. You don't need to, if someone is in US, you don't want the data to be coming all the way from Japan. That will take a long time. So you cache it near maybe a US AZ region so that you can someone can access it faster. Of course, that structure that I've just explained will be secure because first of all, we have the multi-layer. This is the security layer. This is also a security layer. This is multiple VPCs in case one goes down. So we have security on the multi-layer. We also have security on the encryption layer, and at rest, you can do that on the Aurora part of the DynamoDB part. You can do that in Lambda. And of course, you'll have IAM roles to kind of access all this data. You don't just, IAM roles are the equivalent of roles that we talked about. Not everyone. You assign a role. What was the name? Rosie and something?
Rosie.
Yeah, that one. So this is what IAM roles do as well. Secrets manager, passwords, who's accessing what. This would also be highly available if we took it to AWS because first of all, it's in multiple AZs. It also scales. That's what the Auroras and all these things are for. Cross-region replication. That's what DynamoDB is for. This is basically, I think we covered this as well. Not all your data is like one region. All your data is in Europe. They bomb Europe, your data is gone. No. So your data is like with multiple, it's in Europe, but it's reconfigured. Actually, someone put it simply. When you're on YouTube and they're always suggesting the same video, that's because that video is closer to you. Them getting to a different video is like they have to go to a different region, which costs money. So of course, region replication, and of course, we have some disaster recovery strategies in there in the Lambda function as well. It's also to be performance optimized. Aurora replicas can't beat that. DynamoDB DAX, this kind of speeds up retrieval.
Indexes.
Yeah, and of course Elasticache put it closer, CloudFront to kind of like add the speed layer kind of thing. And then you have all these metrics which you can use, CloudWatch metrics they're like querying kind of like to know, how's our data doing, how many records we have, blah 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 blah. So this is all part of the architecture that we built. This is in Kinesis streams or something like that. Why this would be nice? It's scalable, multiple AZs, and also you can actually add in data and we just scale accordingly. Highly available, It's secure, all those roles are ML roles. It's cost efficient because AWS has this thing of well-architected framework. Like Professor mentioned, they actually want to save you money, so they try to give you the best and the cheapest. Compliant, whenever you want to kind of like expand this, you can still do that. Batch processing is capable. That's what all those Auroras and DynamoDBs are supposed to do. And then now, of course, we mentioned earlier we had used the Snowflake kind of, the schema. Yeah, star schema. How would we take this to Snowflake? The key advantages, first of all. Single platform for structure, patient data, semi-structure, medical notes, and data. So there was a question to kind of like take this to Snowflake and why that would be the best. Okay. So single platform for structured patient data and semi-structured medical notes and data. If you're to put this in a Snowflake architecture, you have all your data in like one, because we're tracking multiple regions, so put them in a single platform to be kind of better. Automatic scaling for outbreak scenarios, like Professor mentioned, when it now turns into an outbreak, that will be able to easily scale versus 5 patients who have a cough. Of course, pay per second pricing. That's when you query, you only pay for what you're using. You went through that in the class. Zero copying cloning for testing environments. The same thing of like having your data in multiple. You don't have to kind of like pay for all that. And then the time travel feature, which if you're to scale how bad was this disease that we got, maybe let's say COVID, how bad was the COVID symptoms, let's say 2 years ago, you can be able to do that in Snowflake. These are just some of the healthcare specific benefits if we use Snowflake for our model. Secure data sharing, of course, these are hospitals, these are people's records, real-time outbreak monitoring, we already mentioned that, and then it can easily go into AWS if they need to. And of course, it's cheap. Better resource utilization, like Professor mentioned, you're not buying a computer and it's seated there and yet, that kind of thing. Enhanced analytical capabilities, or that we get if we do this. Now we tried to kind of like, we use sample data, so we tried to kind of plot we ran some queries, got some data, tried to plot some graphs, just because we could. So the first one was total cases.
Is this all on the dimensional model or the operational one or the transactional one?
The graphs?
Yeah. Dimensional.
Yeah. So.
And did you use a tool or for this? Tableau.
Yeah. So again, this is all sample data. So the first disease outbreak analysis, total cases by region for disease outbreaks. We did a bar chart to kind of show you which disease is the most, in what region. This is again sample data, so nothing much, but this is how you could see North region, Dubai, Houston, London having the most outbreaks. Just to also give an idea of the kind of analysis you could do using our solution. Healthcare facility utilization, bed and ICU capacity, like you mentioned, that was a big problem during COVID. So you would need to know, showing who has the capacity to actually take this up. And again, we plotted something to solve this. You see who has the capacity, the bed versus an ICU. You find something like, let's say, Houston, very many bed capacities, but very few ICUs. So you'd be like, okay, I can take people there. Some patient disease severity by gender, who's getting what the most, kind of useful as well. And resource inventory, who has what, so that you know who to send where. And yeah, thank you.
By the way, do you ever pay us stick for that deodorant last?